Hey everybody, we're going to do an example of some parametric equations, and I shouldn't just say this is an example. This is a pretty important example. This is a super common, or at least the base of a very common, let's say, category of parametric equations. So you may have even seen it before, but let's go ahead and do a little investigating. And I'm going to look at the following parametric equations. So we're going to look at x of t equals cosine of t, y of t equals sine of t, right? Remember what our parametric equations are. We're putting in a real number and we're spitting out a pair of numbers. This is just right, this symbol just means all the real numbers. This is just all the coordinate pairs of real numbers. Right, so another way we can write these parametric equations would be cosine of t, sine of t. And let's give this an interval, let's say from 0 to 2 pi. Okay. So I just want to investigate what happens as I start at 0 and go through some values of t. And I want to see what x and y coordinates I get. Right, so then here I'll put my coordinates, right? Because I want to investigate this graph, okay? So I'm going to pick convenient values of t, 0, pi over 6, pi over 4, pi over 3. Let's start with this, right? If we have these values, we know that our trig functions start to repeat. Just there's negatives and positives happening, but we might be able to get away without having to dig too far into those. All right, so all I'm going to do is evaluate cosine and sine at these values, and then put them together to have coordinate pairs, right? So cosine of 0 is 1, sine of 0 is 0, so this is the point 0. I'm just going to go down the cosine ones. It's kind of easier for me if I think through one at a time. So if you remember from a trigonometry class, the cosine of pi over 6 is root 3 over 2. I'm going to give decimal approximations to all of these since I want to graph them. I want to know about where to put these. So then pi over 4 gives us root 2 over 2, which is approximately 0.707. Pi over 3 gives me 1/2, or 0.5, and then pi over 2 is 0, which is already a decimal approximation. And if you remember your trig, these will just be the same values in reverse order. Right, so our points then are going to be 1, 0, 0.866, 0.5, 0.707, 0.707, 0.5, 0.866, and 0, 1. Okay. So I noticed first of all that everything is positive. So let's just try to graph this thing in the first quadrant and see what pops out. Just give myself a little scale. Maybe I'll mark off 1/2 and about 1/4. We're going to do this on a computer in a second, but let's just kind of work through it to build a little intuition. All right, so I start at the point 1, 0. This is my initial point, right? Remember we said when we talked about parametric equations, the value at the beginning of our interval is our initial point. We start there, and we go after pi over 6 seconds have passed, or whatever units of time we're using. We move to the point 0.866. So we haven't moved. Our x coordinate has decreased a little bit. Our y coordinate has decreased quite a bit, somewhere about there. Then 0.707. So now the y coordinate has continued to rise, the x coordinate has continued to go down, and they're equal value. then we get, my scale's quite a bit off, but I'm doing the best I can, and like this, something like that. Okay, so I think this one was maybe a bit, oh, that's why that's way off. I wasn't very careful with those. So this should probably be somewhere more like this. Okay, now I haven't proved anything to you, but you might get the sense that our thing moving through these points, right? I'm getting that kind of motion gives us a hint at what we might be looking at. I'm moving in this direction, okay? Feels like it might be a piece of a circle. And in fact, if you think back to the unit circle definition of sine and cosine, which you should, those are a very good definition of sine and cosine. We've really just used the definition of sine and cosine. They have to be circles. This is how we define the x and y coordinates to be. We start with a circle and define cosine and sine to be the x and y coordinates. We're just going backwards. We're looking at the x and y coordinates of cosine and sine. That's going to be the points on the circle, right? So in the previous, in the definition of sine and cosine, we go from the circle to the x and y coordinates. Now we're going backwards, right, to get to a circle. So this x of t equals cosine of t and y of t equals sine of t is a form of parametric equations you will see over and over and over again. They describe the motion of a circle. We've only gone to pi over 2. As you continue through the values, the same thing keeps happening. It moves all the way around this circle until you get to 2 pi, which puts you back at this point. The cosine of 2 pi is 1, the sine of 2 pi is 0, right? So this point actually is the initial and terminal point for these parametric equations. I'm going to, let's take a look at an animation of this. So that is, there we go. Right, so here we see this beautiful particle traveling around. It's going from 0 to 2 pi. It's just restarting the animation every time it gets back to 0, or to 2 pi it goes back to 0. And so we see this nice circular motion, right? You can see one reason like why these things show up a lot is there are things that we want to describe that have circular motion, things like orbits, right? When you think about planets orbiting or satellites orbiting, right? Complicated versions of what we just did are ways in which we might be able to model that motion, okay? And we've done it the same, what parametric equations always do is we split that motion into two things. The x motion looks like a cosine curve here. The y motion looks like a sine curve. You may have seen something like this showing how sines and cosines come out of circular motion. Let me share something else with you here. Some of you may have seen this before. This is a pretty, I think it's a pretty famous GIF. I know I've seen it show up plenty of times. But in any case, you see how splitting this circular motion in this green circle at the bottom into into its horizontal and vertical motion is related to the sine and cosine functions, right? So this red line is showing us the vertical motion. It's staying with the particle vertically, and the blue line is staying with it horizontally, giving us the cosine, right? They sort of speed up in the middle and slow down as they approach for the cosine, the left and right sides of the circles, for the sine, the top and the bottom of the circle. All right, let's do something else. Let's go back to my animation, right? Let's just look at what happens when we change a couple of things. For instance, what if I were to change cosine and sine to half cosine and half sine? Well, what we end up with is a circle with half that radius, right? So the amplitude of sine and cosine there tell us the furthest left and right or furthest up and down it goes, so we can change the radius of the circle very easily using those things. And all I've done is change the numbers in place of them. Or I can move the circle very easily. If I wanted to move it 1 unit to the right and 1 unit up, I could simply add 1 to each. All right, so it's going off screen now, but I've moved that circle up to its center at 1, 1 by adding 1 and 1 to each of the coordinate functions in these parametric equations. All right, I'm going to go back to the original. I want to do something else with this. Let me get my circle back to what it was. Now I'm going to look at this bottom one where I've got cosine of 2s, sine of 2s. Now I've added a constant inside, or cosine of t, sine of 2t. I've added a constant inside the sine and cosine functions. What will this do? Well, if you imagine, as I increase t from 0 to pi, but I'm multiplying it by 2, I'm going to go from 0 to 2 pi. Or if I go from 0 to 2 pi, but multiplied by 2, I increase from 0 to 4 pi. In other words, I go through these input values twice as fast. So let's put a particle traveling with these parametric equations that have a factor of 2 multiplying the parameter. And we see we get something moving twice as fast. Maybe I'll change the color. It kind of disappears on that. How about black? There we go. That looks pretty good. All right. So I think you can see that black particle is traveling twice as fast. I mean, you might not be able to tell exactly that it's twice as fast, but if you notice when they pass the initial point at 0, 0, right? So our initial point is right here. Notice by the time the blue one gets to the other side, the black one is just finishing, right? So the blue one's traversed half the circle in the time it takes the black one to go through the whole circle. So with these kinds of manipulations, we can describe lots and lots of different kinds of circular or even elliptical kinds of motion. And so that's why this particular set of parametric equations is pretty important to understand. So almost whenever we see circular motion, this is a way that we want to describe it. Okay, that is it for this one. Thanks, everybody. I'll see you next time.